review video is going to serve a couple of purposes. One, to catch you up if you were missing anything this week or last week actually, and two, just to study up on the test that's coming up either Wednesday or Thursday for you. So this is going to be the work in simple machines. And first we're going to start with the definition. Work is simply a transfer of energy through motion. And if you might remember that work is calculated by using force and multiplying that by distance. And work is going to be measured in joules. And anytime you feel like you didn't hear me or need to hear it again, you can certainly pause and rewind, or however you want to do it. You can watch as many times as you want to. Okay, so unless the force applied to an object actually moves or changes its motion, no work is done. So you can push on a wall, but because the wall doesn't move, you didn't do any work on it, even if you were sweating up a storm. So here's a practice problem for you. How much work does a father do if he lifts his daughter 2 meters and exerts a force of 190 newtons? Well, let's set it up. We know that work equals force times distance. In our case, the force was 190 newtons. The distance was 2 meters. And so we're looking for the work. So what we have to do is take the 190 newtons, multiply by 2 meters, and we get 380. And because work is measured in joules, we capitalize it J. Energy is simply the ability to do work or cause change. The unit of measure of joules, of measure is joules as well, just like work and energy are kind of synonymous. Power, rate at which work is done. And you can calculate it by taking the work and simply dividing it by the time. And it is going to be measured in watts. Here's a practice problem. It takes 100,000 joules of work to lift an elevator 18 meters. If this is done in 20 seconds, what is the power of the elevator? Let's set it up. Power equals work divided by time. Work was 100,000 joules. Time was 20 seconds. So we're looking for power. This is going to be a two-step problem. Our power is found by taking 100,000 joules and dividing by 20 seconds. And that's going to give us 5,000 watts. A mechanical advantage, sometimes abbreviated capital M, capital A, it simply measures how much machine multiplies the force or distance. And there are no units of measure to remember on this. It's just a number. The greater the MA, the more work is done by the machine and less by you, which is a good thing. Friction does decrease the mechanical advantage of a machine. And to get around that, again, remember, no machine is going to be 100% efficient. But you can get probably around anywhere from 20 to 30% if you simply apply lubrication, oil, or grease. That will increase the efficiency of the machine and reduce that friction. Mechanical advantage, there's two things. One is if you have an output force, you divide it by the input. Or if you're talking about distance, it's input distance divided by output distance. So here's some more problems. Calculate the mechanical advantage of a ramp that is 6 meters long and 1.5 meters high. The setup, MA is input distance divided by the output distance. Our input distance was 6 meters. Our output distance was 1.5 meters. So we're looking for the mechanical advantage. Our solution is 6 meters divided by 1.5. We're left with 4 with no units. So this particular machine gives us a mechanical advantage of 4, or 4 times more effort exerted by the machine than by you. Another way of thinking about it. Another problem. Calculate the MA, or mechanical advantage, of an automobile jack that lifts a 9,900 Newton car with the input force of 150 newtons. Our setup, MA equals output force divided by input force. Our output force was 9,900 newtons. Input force was 150 newtons. And so we're looking for the mechanical advantage again. Our solution is simply by taking the 9,900 divided by 150, and we are left with 66 mechanical advantage. Again, no units. A machine is simply a device that makes work easier. And of course, as you remember, there are 6 simple machines in no particular order. But we have an inclined plane, a wedge, a screw, the wheel and axle, a lever, and you guessed it, a pulley. Inclined plane, if you would think about a board over stairs, what's in red here is actually inclined plane. It actually increases the distance. And so if you increase distance, you lessen the force amount or less the work you have to do. So it's a slanted surface used to raise or lower objects. Axle or chisel is an example of a wedge. And simply an inclined plane with either one or two sloping sides or surfaces, and it does move. The screw is an inclined plane round around a cylinder, invented by Archimedes. A bolt is also an example. Wheel and axle is a rotating lever that consists of a larger wheel around a smaller wheel. We call that the axle. Okay, doorknobs and pencil sharpeners have wheel and axles. And here's a picture of one. If you think about what's in the center, the green, that is actually the axle, and the outer part, the orange or orangish red, is the wheel, the wheel part. Now, the bigger that wheel is, the easier it is to turn, so that increases the mechanical advantage the larger the wheel becomes. Pulley is simply a rotating lever that consists of a wheel that either has grooves for rope, chain, or cable to go between. And here is a picture of one. This one actually has 1, 2, 3, 4, 5, 6. Yeah, 1, 2, 3, 4, 5, 6, 7 wheels. A lever, bar that pivots about a fixed point. And a simple machine can do three things for you. One, it can increase or multiply force. It can increase the distance, like an inclined plane. Or it can change the direction of a force, like a pulley. The fulcrum is where the lever attaches. In this case, it's a blue triangle. And it's a fixed point on a lever. Now, there are three types of levers, first class, second, and third. The first class is almost like a seesaw, where the fulcrum's in the middle, the input force is on one side, the output force is on the other. And so as you push down on one end, the opposite end goes in the upward direction. These include seesaws, boat oars, and crowbars, which is what's pictured. The second class lever, fulcrum is on one end, the input force is on the opposite end, and the output force is in, well, not really the center, it can be, but anywhere between the output force and the input force. An example would be a wheelbarrow. A third class lever changes magnitude of a force, and the fulcrum is actually on one side, the output force is on the other, and input force is somewhere in between those two. And this one changes the magnitude of a force. Now, a broom or a rake, as this picture depicts, is an example of a third class lever. Compound machine is simply a combination of simple machines where it has two or more. Think of a bicycle or a car. Efficiency. This is simply a percentage, and it tells you how much energy is converted from the input to the output of the machine. Again, there's no such thing as a 100% efficient machine, but you can find it by taking the output force or the work output and dividing it by the input force, and when you multiply that by 100, and it is expressed as a percentage. Get rid of this. All right, the practice problem. When you do 100 joules of work on the handle of a bicycle pump, it does 40 joules of work pushing the air into the tire. What is the efficiency of the pump? Well, here's your setup. Efficiency equals useful work output divided by the work input. Multiply that by 100. Where our work output was 40 joules, and our input was 100 joules. So we're looking for the efficiency. Well, if you take 40 joules and divide that by 100, and whatever that gives you, multiply by 100, you'll get an efficiency of 40%. This concludes the review. You can certainly watch this again as many times as you need to, and rewind and stop if I went too fast.